All right, welcome back, everyone. For our final little discussion here, we're going to talk about Bose-Einstein condensation. Um, and we've been looking at the behavior of bosons for the last couple of lectures. Both the photons of the black body electromagnetic radiation and the phonons of the Debye theory. Both of those cases, the particles, if we want to call them that, are Bose particles. They have obey Bose statistics. The Planck distribution is essentially the Bose-Einstein distribution for the limit of chemical potential is zero. And in this case, in these cases, because those particles are essentially um, uh, excitations of, in the radiation case, the electromagnetic field, and in the phonon case, those are vibrational mode excitations in our crystal lattice. In both cases, those excitation particles are massless. They don't have any rest mass because they don't exist in a not moving form. They are vibrations, they are wiggles, they are disturbances in a medium, either the electromagnetic fields of the universe or the crystal lattice of a solid. And as such, they don't have a chemical potential. You can generate vibrations out of nowhere, and you can dispose of vibrations out of nowhere as long as you're pulling the energy into and out of those vibrational modes. There's no other energy associated with it. There isn't any chemical potential. But if we're talking about massive particles, particles that have mass, they don't have to be particularly heavy particles, but particles that have mass and are bosons, then the chemical potential isn't necessarily going to be zero. It probably isn't going to be zero in the most general case. So what do we do outside of Planck distribution? How are we going to actually deal with the full-on quantum behavior of bosons? So what we're going to look at today is the most famous effect of Bose particles, which is that at very low temperatures, you can generate a Bose-Einstein or a Bose-Einstein condensation, that your material can condense and form a highly degenerate material where all of our, or a large fraction of our particles all have the same quantum state, various superfluid states, superconducting states, and so on. So we're going to look at the very, very low temperature limit. Now we're going to limit ourselves here to talking about particles who are which in the classical limit would obey the ideal gas law. So non-interacting particles. We're not going to be able to look at interacting particles at the sort of limit that we're talking about here. That requires a huge amount of heavy lifting from the quantum mechanics side, and it's really just beyond the structure of this course, is beyond the scope of this course to get into it. But we'll give you get a taste of what's going on with Bose-Einstein condensation, and see if we can try and both see that it actually happens, at least in the case of non-interacting particles. We'll use as an example one of the first detections of this condensation, which was from a collection of rubidium-87 atoms trapped in a very small box at low temperatures. And so as we go through this, we'll take a look at that particular example as well. So to start with, let's look at the temperature equals zero limit, like we kind of like we did for the for some of our earlier studies, and then we'll go beyond the temperature equals zero. So at the temperature equals zero limit, it's very easy to understand what's going to happen. all of our atoms are going to try and find their lowest energy state. They're going to be in their lowest energy state. And since there isn't any Pauli exclusion principle for bosons, that means that all of the atoms will be in the ground state for a single atom. So for atoms in a box, the energy of the ground state can be written E naught is Planck's constant squared over 8mL squared times the 3 nx, ny, and z, all of which are 1 squared. So this is just 1 squared plus 1 squared plus 1 squared is 3h squared over 8mL squared. And for any reasonably large L, right, so as our box is not quantum scale but large, then this energy is going to be tiny. So in the case, for instance, of our rubidium atoms, so for our RB87 atoms, the ground state energy is going to be, again, 3 times Planck's constant, 6.63, 10 to the minus 34 joule seconds squared over 8 times the mass, which is 87 times the atomic mass unit, 1.66, 10 to the minus 27 kilograms, times L squared. And in this case, the box is a cube with an L of 10 to the minus 5 meters. So this is 10 to the minus 5 meters squared. And if you plug all that together, that gives you 1.14 times 10 to the minus 32 joules, which is also 7.1 times 10 to the minus 14 eV. So yes, indeed, the ground state energy for a single atom of rubidium-87 is tiny, as we expected. So those are very, very low-lying energy states indeed. If we then plug this into the Bose-Einstein distribution, we can find that the number of particles in that ground state would just be expected to be 1 over e to the minus, or e to the energy of the ground state minus whatever the chemical potential is over kT minus 1. And for small temperature, this is going to approximate 1, and if we expand it as a Taylor series, then we can approximate e to the x as just 1 plus x, so that what we get out of here is that our e to the epsilon naught minus mu over kT, so energy of the ground state minus chemical potential over kT, is approximately 1 plus energy minus chemical potential over kT, or that in other words our occupation of that ground state would be expected to be 1 over 1 plus E naught minus mu over kT minus 1. Well, the 1 and the minus 1 cancel, and this just gives us kT on the top, and the difference between E naught, our ground state energy, and our chemical potential. So at t equals 0 exactly, this is going to go to 0, and the only way that we're going to get non-zero occupation anywhere is if this also goes to 0. So the chemical potential must equal the ground state energy exactly at temperature equals 0. And just above temperature equals 0, then this must be just slightly less than the ground state energy, so that we get appreciable numbers of particles in that ground state energy. So the behavior that must be true is that just above absolute 0, the chemical potential of our Bose-Einstein gas must be just barely less than the energy of the ground state. In general, we could write that the total number of particles in our system is just the sum over all of the states of, again, the Bose-Einstein distribution, e to the energy of that state minus chemical potential over kT minus 1. And this equation is essentially how one in principle could determine the chemical potential, right? So this constraint, if we have a fixed number of particles, if you add up all of the possible states those particles could be in, then this essentially is a normalization integral or a normalization sum, and is a definition, or it determines the chemical potential. The problem is that it determines the chemical potential in a way that is particularly inconvenient to pencil and paper analysis. You could guess a chemical potential, and then check to see if you got the right number of particles, and then guess a different chemical potential and check to see if you got the right number of particles, and iterate until you get the correct number of particles. And if you had a computer, you could do that. And you might not be too long in getting to it, as long as your first guess was pretty good. But it's not going to be easy. In practice, at least sometimes, it's convenient to convert this sum to an integral, so we could try that. So we could convert this to an integral of e, or from 0 to infinity, of the number of states, or the density of states at a given energy, and then integrate over all the energy states, energy minus chemical potential over kT minus 1, integrate this in energy. As long as kT is much, much larger than the energy of the ground state. So in other words, as long as we have temperatures that are way above the ground state temperature, or the kT for the ground state, then the number of discrete terms in this is going to be relatively small, and so we might be reasonably able to do this approximation. In our case, the the density of states is almost the same as the density of states we had for the electron gas calculation, except that for our spin 1 state, there's only one, except for our bosons here, there's only one spin state as opposed to two, so our density of states is down by a factor of 2. In this case, it's just 2 over square root of pi times 2 pi m over h squared to the 3/2 times the volume times the square root of energy. So again, this is almost the same form for the density of states that we saw in the electron gas calculation. And so we could plug this into our number calculation and see if that helps. So this gives us a 2 over root pi and then 2 pi mass over Planck's constant squared to the 3/2 times the volume, and the integral from 0 to infinity of square root of energy d energy over e to the energy minus chemical potential over kT minus 1. Problem is that doesn't integrate analytically. If we know the chemical potential, we can integrate that numerically. Or again, we could guess the chemical potential, integrate this numerically, see if we got the right n, and repeat until we iterate until we could find the chemical potential. But there isn't a nice closed form way to invert this and write down the form of the chemical potential in terms of the number density, or the number of particles. So, one thing we do know about the chemical potential is that, again, if we're anywhere near something like a Bose-Einstein condensation, where we have an appreciable number of particles showing up in that lowest energy state, then the chemical potential, as we saw earlier, must be just a little bit less than the ground state energy of our single particle state. And that ground state energy of the single particle state was itself very, very small. So we know that the chemical potential must be very, very small. We could guess, as a guess, what about chemical potential equals 0? That's a very small chemical potential. Well, what happens if we put chemical potential equals 0 in here? Well, let's find out. In that case, then our integral does in fact turn into something we can evaluate analytically. So we've still got the same constants out front. Now we've got the integral of the square root of energy, d energy over e to the energy over kT minus 1. And again, we can do our usual trick, turn that exponent into our change of variables. So we set x equal to energy over kT. And that gives us a new version of this equation, 2 over the square root of pi, now 2 pi m kT over h squared to the 3/2 times the volume, and now we're integrating from 0 to infinity square root of x over e to the x minus 1 dx, and this gives us 2.315, which, plugging in with a bunch of the constants up in front, gives us that the number of particles is 2.612 times the thing in the parentheses, 2 pi mkt over h squared to the 3/2 times the volume. And herein lies the problem with assuming chemical potential 0, which is that the only thing on the right that depends on the temperature is the explicit temperature dependence, so that the number of particles goes as temperature to the 3/2. So in other words, as you change the temperature, you're inventing particles out of whole cloth. Well, obviously this is nonsensical for particles of significant rest mass. The temperatures here are low temperatures, not things where you would expect particle-antiparticle pair production. And we should have expected this, because this is exactly the behavior we saw with the mu equals 0 systems of photons and phonons. But in this case, obviously, this is not correct. On the other hand, it's correct for at least one value of temperature, right? There is some temperature for which this will give us the correct number of particles. And indeed, we could invert this and solve for that temperature. We'll call it the critical temperature or condensation temperature, Tc. And KTC is just 0.527 h squared over 2 pi times the mass times n over volume to the 2/3. So we inverted this equation to give us this equation, which is essentially a definition of our condensation temperature. So why does this break? What happens just above and just below the condensation temperature? Well, as we go above the condensation temperature, what happens is that the chemical potential becomes larger and negative, which means when we go back here, if the chemical potential gets large and negative, then this exponential term stops being positive, or it becomes e to some large positive number on the bottom, and our states get or the population of that lowest energy state becomes very small, because we start populating higher energy states, and essentially our Bose behavior stops being the interesting condensation behavior. For temperatures below this condensation temperature, then we've got the situation where our approaching this as an integral doesn't really work anymore. And the reason is, if we look here at this diagram, over here we have the density of states, which, as it did in the free electron case, the density of states is going up as the square root of energy. But for low temperatures, the Bose-Einstein distribution becomes essentially asymptotically infinite at low energies. And what we're integrating is the convolution of this extremely sharp distribution multiplying this much slower changing distribution, and basically you get a hugely sharp edge which doesn't really capture correctly the summation that needs to be happening, the discrete summation that needs to be happening down in those lowest energy states. Treating this as an integral for temperatures below the condensation temperature doesn't work very well, because the terms in those sums are going to start to be dominated by, well, at the very least, that ground state term, that first term, and potentially several terms above it. So treating this as an integral just becomes invalid below this point. So one thing we could do is replace that sum, right? So for low enough temperatures, if we go below the critical temperature enough, then the only one of those discrete sums in this summation equation, the only one of those discrete sums down there that should really matter outside the integral would be that first ground state. And so we could use this integral to approximate the excited states as 2.6 or 2.612 times 2 pi mkt over h squared to the 3/2 v for T less than this critical temperature. And in other words, that the number of excited states is T over Tc to the 3/2 times n. So we normalize this to the one temperature we know it works, and then we can calculate as a scaling relation, because temperature goes at, or the number of excited particles goes as T to the 3/2. And now it's okay that the number of excited particles isn't constant, and indeed we should be increasing as the temperature is increasing, because a few of those particles are getting out of that ground state. And then the number of particles in the ground state would just be n minus the excited ones, and that's going to be 1 minus T over Tc to the 3/2 n. This will work best in the region where we are not immediately below the critical temperature, or at least this will work the least well as a prediction just below that critical temperature, where it might not just be the first term, but might be 2 or 3 or 4 terms, or however many terms that are excited, that are significantly populated down there. All right, well, let's take a look at some of these calculations in the context of our rubidium-87 atoms. So if we have, again, if we have 10,000 rubidium-87 atoms in our 10 to the minus 5 meter cubed box, then K times the critical temperature is 0.527 times h squared over 2 pi m number of particles over volume to the 2/3. Now we could rewrite this slightly. We could turn that v back into an n and l squared. So v to the 2/3 is l squared on the bottom. So that's going to give us 0.527 h squared over 2 pi ml squared n to the 2/3. And if we manipulate things just slightly, this is 0.527 times 4 over 3 pi 3h squared over 8 ml squared n to the 2/3. And the reason for doing that is that this is the energy of the ground state. So we could write kT here in terms of the ground state energy. It's 0.224 n to the 2/3 times the ground state energy. And so for our rubidium-87 atoms, that's KTC equals 0.224 10 to the 4th to the 2/3, and our ground state energy, this comes out to be about 104 times the ground state energy, which was 104 times our ground state energy, which was 7 times 10 to the minus 14 EVs, which gives us a KTC of 7.4 times 10 to the minus 12 EV, or a critical temperature of 8.6 10 to the minus 8 Kelvin. Pretty damn cold. Indeed, the experimental result was that significant portions of the rubidium-87 started condensing down at around temperatures of 10 to the minus 7 Kelvin, which is in rough agreement here with the calculation we just made. So in general, using this mechanism, we can calculate a critical temperature for a given number of particles, and then use that scaling relation that the number of excited particles equals T over Tc to the n. So you use the number of particles to calculate Tc. Once you know Tc, then you can you can predict that the behavior of the ground state should go as 1 over T over Tc to the 3 halves times n, and that the number of excited states goes as T over Tc to the 3 halves. And if we plotted this in terms of so n naught, the number of atoms in the excited state, if this is our critical temperature, this goes something like so, and the excited states would look something like that. And you see, as we get below the critical temperature, we start getting large numbers of particles showing up in the ground state and not so much in anything else. And once you know the number of particles in that ground state, then you could also go back to our relationship that once we know n naught, we go back to the calculation we made it earlier, which is that n naught is roughly kT times epsilon naught minus mu, minus the chemical potential. You can then invert this for chemical potential and use this to solve for chemical potential as a function of temperature. And what you find is that essentially, again, as you hit that critical temperature, the chemical potential starts dropping off, and that just below the the critical temperature, the chemical potential here is very, very close to that ground state energy, just sort of lying right below it. All right, so this is sort of a rough model that has some degree of validity for non-interacting particles at very, very low temperatures, forming Bose-Einstein condensates. The last little piece of this chapter, the author goes into the question of what exactly is happening. Why is it that this condensation happens? And it turns out that the answer is primarily because of the quantum nature of indistinguishable particles. If we imagine that the particles were distinguishable, then we could treat each particle as an independent system and then use Boltzmann statistics on that independent system, and the number of states that would be available is large, roughly the single particle partition function for the number of states, and so the likelihood of being in the ground state is very small, something like 1 over the single particle partition function. So those individual particles wouldn't show up in a Bose-Einstein distribution. Now, if we looked at that not from the point of view of the individual particles as our system, but as all of those particles in our system, then the energy of our system, well, we would know, again, because our particles are going to have average thermal temperature kT, so our thermal energy is going to be something like nKT, and thus the Boltzmann factor for our system will be something like e to the minus nKT over kT, or something like e to the minus n. That's a tiny number, and so why is it that we don't have gigantic numbers of distinguishable particles forming into the ground state? And the answer is that the number of different ways that you could arrange a very large n number of distinguishable particles is gigantic. Indeed, it dominates that even that e to the minus n is completely swamped by just the number of ways that you can arrange n particles, where you can tell the difference between every n particle. Because the number of particles, or the number of ways to arrange those particles, is something like the single particle partition function to the nth power. And that's going to totally dominate our e to the minus n. And so for distinguishable particles, you don't get a Bose-Einstein condensate. But as soon as our bosons become indistinguishable from one another, then the number of ways that we can organize those kT energy states becomes quite a bit smaller. The number of states becomes something more like n plus the single particle partition function minus 1, choose n. In other words, it becomes a combinatorics problem, not a z to the n problem. And indeed, this could be approximated either as e to the z Ez over n to the n for z dominating n, or e to the n over z to the z for a partition function much smaller than the number of particles. So if the number of states for a particular particle, for a single particle, is at our energy kT is smaller than the number of particles, and these solutions will be familiar. They're the same solutions essentially that we saw for the Einstein solid in the high and low temperature limit. So when the temperature gets cold and the partition function for a single particle gets relatively small, then this is much less than 1, and this term is not large enough that the e to the minus n term is completely swamped, because n to the z is not going to beat out e to the n in the case where z is much less than n. And so we do have then all those upper levels being exponentially crushed by the Boltzmann factor, and we go back to the only available state, essentially, that anybody can populate with any degree of with any, or to any extent, is that lowest energy ground state. So the practical upshot is that Bose-Einstein condensation is deeply tied to the quantum mechanical nature of indistinguishability, and indeed the fact that we can observe Bose-Einstein condensates means that quantum indistinguishability is a real phenomenon at the fundamental. It's not a hidden variable thing. It's not that a statement about the limits of our knowledge. It's a statement about the physical nature of the universe, that quantum indistinguishability is a real phenomenon, not just a statement about our knowledge. It has to do, it's tied into the notion of exactly what the nature of quantum uncertainty and quantum fuzziness is, quantum indistinguishability. And indeed, those particles are in fact completely defined by their quantum numbers, and we can't tell the difference between them. There aren't different flavors of those bosons. They are all exactly identical. Nothing can tell them apart. All right. Well, that's all we're going to cover here. There is a further chapter in the text. Chapter 8 goes into looking at some of the behavior of systems when there are interactions between particles. Again, the piece of what we were just talking about that we left out. We're not going to try and cover that in this class. The book only does the barest introduction of that stuff. It's interesting going. If you're feeling up to checking it out, I encourage you to do so. It is interesting stuff. It gets fairly hairy fairly quickly, which is again why, you could cover many textbooks worth of this material of the quantum statistics at the many body problem or condensed matter physics end of things, but that's really a different course. That's where we're going to stop here. And it has been my pleasure to be your tour guide through this semester, under not ideal circumstances, obviously. And I will be putting up later this week, I will be publishing a final exam, which is going to be much in the same manner as midterm 2, a sort of long-form take-home exam for some problems to try out that you upload again to Canvas in the usual manner. I wish you all the best on this final and your future finals and everything else going forward.